Welcome to the new chapter, chemical bonding. That's a fourth chapter of your 11th chemistry. Okay, and this is a basic one, and have a lot of application in inorganic chemistry for the bonding. Okay, so let me start the chapter. Ready? So first of all, let me define what is a chemical bond. What is a chemical bond? Okay, so write down. A chemical bond is the force of attraction between constituents like atoms, ions, molecules in a chemical compound. Okay, that means if you have a chemical compound, say sodium chloride. Okay, we all know that between the Na plus and Cl minus, there is some kind of force of attraction. That force of attraction, what we call as ionic bonding. Ready? Fine. The next, that is, listen. I have methane. Carbon surrounded by 4 other atoms. Okay, and some kind of force are there which hold these two atoms, and that force is said to be covalent bond. Okay, ready? If I have a complex CrH2O 6 times of 3 plus, ready? And the chromium, which is surrounded by 6 H2O molecule in a particular geometrical fashion, say octahedral, whatever it may be. Here, the molecule water, which is surrounded by chromium by means of a force of attraction. Okay, it is held around the chromium by means of a force of attraction. That force of attraction is said to be coordinate bond. Okay, and if I have a metallic crystal where it consists of a lot of positively charged body called kernels, in which electrons are, or kernels which is surrounded in a sea of electron. Okay, where these particular kernels are held by a force of attraction, and that force of attraction is said to be metallic bonding. Okay, so chemical bond is a force of attraction which can hold various constants. The constant may be 2 ions, or it may be 2 atoms, or it may be 2 molecules, or it may be 2 any chemical constants which is held by any kind of force of attraction. Then the force of attraction is said to be chemical bond. Okay, basically there are 4 different types of chemical bonds. Okay, 4 different types of chemical bonds. And in our discussion, there are 4 different types of chemical bond. Okay, so let me define. First of all, let me define the relative strength of chemical bond. Relative strength of chemical bonds. Okay, so there are 4 different types of chemical bond, in which the ionic bond is a most stronger. Okay, then the second one, which is given to the coordinate bond. Okay, and the third one, and that is to the covalent bond, and the fourth one, that is little bit weak, that is metallic bonding. So these are the different types of chemical bonds and their relative strength. Okay, fine. So we will discuss the each bonding. Ready? In the following section. First of all, now we can discuss some theories of chemical bonding. Okay, so theories. Ready? And the first theory, or the first attempt about the bonding, that is Coastal-Lewis approach. What it is? Coastal-Lewis approach. Costello-Lewis approach. Ready? Fine. So write some points. The first point. So that's a view of scientists called Costello and Lewis. Okay. So the first point. Atom considered as an arrangement of. First point. Atom considered as an arrangement of kernels and atom considered as an arrangement of kernels plus outer shell. Kernels plus outer shell. We all know that this is chemical bonding, but the bonding of an atom that depends on the valence electron. Okay, so the outer shell, the valence shell, have a greater role in compared to the total number of electron. Okay, valence electron have a greater role in chemical bonding. Okay, so atom considered as two parts, that is kernels and outer shell. Okay, so you copy this also in there. What do you mean by kernel? Kernel means there is inner shell plus nucleus. Kernel is nothing but the nucleus followed by inner shells and the outer one. Okay, so actually atom is a nucleus, inner shell, outer shell. Fine, that's okay, which means kernels plus outer shell. Okay, this have a role here. Ready? So this is the second, first idea. What about the second idea? Second idea, okay, so kernels have no role here. Outer shell is to determine the property or the bonding of a molecule. Okay, so what about the view of outer shell? So there is the next point. Outer shell imagined as a cube with outer shell imagined as a cube with 8 corners around kernel. Okay, so your kernel is here. This is the kernel, and around this kernel, they imagined a cube with 8 corner. Cube with 8 corner. Where this is the kernel, and the kernel which is surrounded by a cube with 8 corners, where the cube with 8 corners is referred as the outer shell. So outer shell is imagined as a cube with 8 corners. Okay. Inside the cube, there will be the presence of kernel. Okay, fine. So that is the next point. Outer shell imagined as a cube with 8 corners. So moving to the third point. Third point. Third point, that is, write down. Third point. So what about the outer shell electron? This cube is said to be the outer shell. So the outer shell electrons which are arranged in the corners of the cube. Outer shell electrons are arranged in the corners of the cube. Okay, so the next point, that is, outer shell electrons are arranged in the corners of cube. Corners of cube. Okay, fine. Fourth one. If you know that how much corners are there for a cube? 8 corners, fine. So all corners are occupied means the atom where its outer shell composed of 8 electrons, because 8 corners are there, so 8 corners occupied means 8 electrons are occupied, which means the atom is stable, right? If anyone have 8 electron in outer, then the basic idea that is stable, fine. So that is also given by the Costello and Lewis. Okay, so if all 8 corners are occupied, then the atom said to be stable. If all 8 corners are occupied, then the atom said to be stable. Okay, you know why it is stable? That is nothing but octet stability. So write one more point, that is the fifth statement. If an atom do not have a complete corners, if an atom have any vacant corner, then the atom try to fill that vacant corner, then only it get stability, then only it get 8 electron in the outer. Okay, so why the atoms are combining with other means? They are combining with the other atoms for what? For they're combining with other atoms for completing the all 8 corners with electrons. Ready? So that is the last point. Atoms combined with other to occupy the all 8 corners with the electrons, which means if they can occupy the all 8 corners with electron, means the atom have 8 electron in the outermost shell. so they will be stable. So for getting stability, they are combining. And these all are the concept by Kossel and Lewis. Okay, I think you know the idea of Octet rule, which means if outer half 8 electron, then it is stable. That concept in earlier days, it is visualized like this. Okay, kernels, valence electron, the cube, outer shell electrons in the corners of cube like that. Okay, fine. And this is later defined as in a normal version called, or in a theoretical version called octet rule. Okay, so the exactly same idea, which is later defined as the concept octet rule. So write down octet rule. Octet rule. Okay, fine. Octet rule. Ready. So the credit for octet rule is given to the very same scientist, Kossel and Lewis. Okay, so octet rule proposed by Kossel and Lewis. Proposed by Kossel and Lewis. Okay, and what is octet rule? It is nothing but atoms are usually combining to fill 8 electron in their outer shell, which means octet in their outer shell. The very same concept which is already discussed in the previous section, that is defined as octet rule. Okay, octet, the term means 8 electron, fine. So you define that atoms combine to form compounds to make octet in their outer. To make octet in their outer. Ready? To make octet in their outer, in bracket of the octet, to make octet in their outer. After octet, you place 8 electron in the bracket, then in the outer shell. In the outer shell. So that is said to be octet rule. Ready? Fine. Okay. And that is called the octet rule. Fine. Now we can discuss some basic ideas. You have to know the valency and valence electron of each atoms. Ready? Then only we can proceed to the next section. Ready? So let me define the two terms, valency and valence electron. Okay, number one, valence electron, let it be small n. Valence electron, let it be small n. Valence electron, small n. Okay. So define that. What is a valence electron? Nothing but it is outermost electron present in an atom. Okay. Valence electron is the outermost electron which present in an atom. So write down. It is the outermost electron which present in an atom. Okay. So the next term, that is valency. Valence. What is valency actually? Valency is the combining capacity of an atom with a hydrogen. Okay, what is the combining capacity of an atom with hydrogen? That is simply defined as valency. So write down, it is a combining capacity of an atom with a hydrogen. Okay, and you can show some examples. Aluminum have a combining capacity with hydrogen, that is 3. And you know, aluminum can exist as AlS3. So the valency of aluminum. Aluminum, the valency is 3. Okay, fine. Oxygen have a combining capacity with hydrogen, that is, can combine with 2 hydrogen to form OH2 or H2O. So the valency of oxygen is defined as 2. So actually the valency is simply, the actual definition of valency is the combining capacity of an atom with the hydrogen. Ready? Fine. And the relation, that is, if n is the valence electron, valency may be, if you know valence electron, then valency may be either n or 8 minus n. I think that you know. If n is the valence electron, then the valency may be either n or 8 minus n. Okay, fine. So now let me create a table, and that is very important, for the valency and valence electron of some group elements are given. Okay, that's very important. Fine. So let me create a table. Fine. And here is the group. Here is elements. And it's valence electron. The last column, there is one more column, which is for valency. Okay. Let the group is group number 1. Group number 1, 2, 13, 14, 15, 16, 17. And one more is the group number 18. Okay. So first of all, you have to know the elements. Okay. So group number 1, first group, we know that lithium, sodium, potassium, rubidium. Okay, that's enough. Cesium is there, that's enough. And for the valency or the valence electron of the first group, that is 1, have 1 electron in the outermost shell, or the valence is also 1. Okay, because we know that the formula, either valency will be equal to n or it is 8 minus n. Fine. What about the second group? That is beryllium, consists of beryllium, magnesium, calcium, strontium. Enough. Valence electron is 2, valency is 2. Okay. The next is 13th group. You know, main group elements are discussed here. Okay. Which means S and P block elements. Ready? So the next 13th group, where you have to know boron, aluminum, gallium. Enough. Boron, aluminum, gallium. Boron, aluminum, and gallium. Okay, the valence electron is 3, valency also 3. Next is 14th group, carbon, silicon, germanium. Enough. Valency 4, valence electron also. Valence electron 4, valency also 4. Is it okay? Fine. Now the next. The next, that is 15th group element. 15th group, nitrogen, phosphorus, arsenic, valence electron 5, valency 3. Nitrogen, the outermost electron is 5, but the combining capacity of hydrogen is only 3, you know, NH3. Nitrogen can combine with 3 hydrogen at a time. Okay, so the valence is 3. Oxygen, 16th group means oxygen, sulfur, selenium. Enough. Valence electron 6, valency 2. 17th group, fluorine, chlorine, bromine, iodine. Enough. Valency 7, valence electron 7, valency 1. Okay. 18th group elements which are able to form compounds in 18th group, that is xenon, radon, krypton. Valence electron is 8. Usually they can't make a bond with the hydrogen. Okay, you know the definition of hydrate. Hydrate are the binary compound of hydrogen with all elements except noble gas. Okay, so the valence electron, valency of hydrogen, noble gas, we can consider it as 0 because the combining capacity of noble gas and hydrogen, that is 0. Okay, so from here the formula 8 minus n, and up to this much the formula n. Okay, this is very important. This is very important. Okay, you have to study this by heart. Ready? That's very important. And you know, in this chapter you have to know what is the valence electron of nitrogen, 5. What is the valency, 3. Okay, so that will be thorough. Ready? So what is the valence electron of oxygen? That's 6, valency of oxygen 2. Okay, so keep it. Moving to the next concept, that is given heading. Lewis dot representation. Lewis dot representation. Lewis dot representation. Okay, Lewis dot representation. and write a point. Write that it is a representation of valence electron of an element using dot or cross. Lewis dot representation. Lewis dot representation, and write that concept. It is a representation of valence electron of an element either by dot or by cross. Either by dot or by cross. Okay, representation of valence electron of an element either by dot or by cross. Ready? And give some example. Let the valence electron of oxygen. What is the valence electron of oxygen? 6. So that 6 electron we can represent like this. Valence electron of sodium, that's 1. And the electron we can represent it using cross also. Either you can use dot or you can use cross. Okay, valence electron of aluminum, that is 3. So you can represent the 3 electron like this, or that's up to you. You can represent 2 electron here and 1 electron here. Okay, whatever it may be. And this is said to be Lewis dot representation. Okay, fine. So now you know what is octet rule, what is Lewis dot representation, like that. So let me let me discuss the 4 different types of bonding. Okay, ionic, coordinate, covalent, and metallic. Ready? So number 1, ionic bonding. Ionic bonding. Ready? Fine. So number 1, ionic bonding. Is it okay? Ready? So in ionic bonding, there are some alternate names for ionic bonding, that is electrovalent bonding, or non-directional bonding. Non-directional bonding. Okay? Ready? The first point, proposed by causal. Proposed by causal. And you all know that how an ionic bond is formed. Okay, it is between the transfer of electron from one atom to another. Ready? So write that. Formed by the transferring of electron from one atom to another. Formed by the transferring of electron from one atom to another. Complete transferring of electron from one atom to another. Ready? Fine. Usually, atom, the next point, which donate, like atom which donate the electron, that will be a metal. Okay, metal of group 1, 2, 13, etc. Like aluminum. Ready? Usually. The next point, usually the atom which accept that particular electron, that are usually non-metal. Non-metal means non-metals of group 15, 16, 17. Ready? A metal which can lose electron to form a cation, and non-metal which can gain electron to form anion. Fine. That's the idea. Ready? Next point. Electrostatic force of attraction exists between them. Electrostatic force of attraction exists between them. Okay. You know that if there is a metal and non-metal, when your metal loses an electron to the non-metal, what happens? Metal become N plus. Or if that non-metal gains an electron, that non-metal become N minus. And the force of attraction between that oppositely charged body, this is a N plus charged, positively charged body, this is a negatively charged body, and that force of attraction, you all know that force of attraction between oppositely charged bodies in a particular distance, that is electrostatic force of attraction. So KQ1, Q2 divided by R square is the force of attraction. Okay, this is a force of attraction actually developing here. Fine. That is said to be electrostatic force of attraction or Coulombic force of attraction. I think you are familiar, that is in physics. Okay. Next idea. Right, next point. And we know that there is a transfer of electron, right? Where metal loses electron and non-metal gains electron. Ready? And that how much number of electron lost or gained, that is said to be electrovalency of that element. Okay. So next point, electrovalency. Okay, electrovalency. It is the number of electron lost by metal or number of electron gained by non-metal. It is the number of electron lost by metal or number of electron gained by non-metal. Is it okay? So let me show some ionic compounds using Octet Rule. Okay, and there we can find the electrovalency or like that. Ready? So let the first one, that is magnesium and oxygen. How the ionic bond formation between magnesium and oxygen? Magnesium have a valence electronic configuration of 282 because the atomic number of magnesium, that is 12, atomic number of oxygen, that is 6. It's not 6. Yeah, that's 8. Ready? So oxygen have electronic configuration 2,6. What about the case? This is a valence electron, right? Okay. If these two electrons are dropped by magnesium, then the magnesium have a valence configuration of 8. So it get an octet stability. What about the valence shell of oxygen? Oxygen have only 6 electrons. If oxygen is able to gain 2 electrons, what happened? Then the oxygen also get stability. So magnesium have a tendency to lose 2 electrons, whereas oxygen have a tendency to gain 2 electrons. So there will be adjustment between magnesium and oxygen, where magnesium donates 2 electrons and oxygen readily accept that 2 electrons to form the ionic compound. And it will be where the magnesium, when it loses 2 electrons, become Mg2 plus, and oxygen, when it gains 2 electrons, become O2 minus. Okay, there exists electrostatic force of attraction, and this typical type of bonding would be called as ionic bonding. Okay, what about the net effect? If the 2 electrons are dropped from magnesium, then magnesium attains octet stability, and if 2 electrons are gained by oxygen, then oxygen also get octet stability. So both are okay. Ready? And this type of ionic bonding is called divalent bond. Divalent. Where 2 dies are represents the number of charge of each cation and anion. Di positively charged and di negatively charged, right? Fine. And what about the electrovalency in these two cases? Here the electrovalency 2, here also the electrovalency 2. Because the number of electrons lost by the metal magnesium, that is 2. The number of electrons gained by oxygen, that is 2. Okay, fine. So this is how your MgO formed. So let me define the next category. That is a compound formed between calcium and chlorine. Calcium and chlorine. So what about the configuration of calcium? 2882. That is the configuration of calcium. Bohr configuration. Okay. And what about the configuration of chlorine? 287. Ready. And calcium have to drop 2 electrons, then only it can obtain a octet stability. But the chlorine have to accept 1 electron. So in your calcium have 2 electrons, but chlorine there is only 1 electron. So if there is an ionic bonding between calcium and chlorine, then calcium need to drop 2 electrons. Okay, but the chlorine have to gain only 1. So chlorine should bring another chlorine also, then only it can accept that 2 electron. Then only they form the ionic bond. So here a losing of 1 electron. Calcium which loses 1 electron to this chlorine and also to this chlorine. Okay, so calcium which have a stability of 288. Similarly, there is 2 Cl minus and both Cl minus attain a 288 stability. Okay, and this ionic bonding is another type of ionic bonding. This is actually dimonovalent bond. Okay, what about the electrovalency of calcium? What is the number of electrons dropped by calcium? That is 2. What is the electrovalency of chlorine? Chlorine means that's doesn't mean that 2 chlorine. Simply the species Cl. Okay, well Cl the species accept only 1 electron. Okay, to make up that problem, here we have to drop 2 electron, but acceptance is only 1 electron. So to make up that problem, we introduce 2 more chlorine, right? Okay. So what about the case in AlF3? AlF3. So aluminum, that is 2A3. Sorry, it's not AlF3. Write in this pattern Al and F. Okay, aluminum atomic number 13, so that is 2838. Fluorine atomic number 927. So aluminum have to drop 3 electron, but at a time fluorine can accept only 1 electron. So fluorine should bring 3 more fluorine like this. So aluminum can distribute its electron to each of them, and that forms Al3 plus 3F minus. Okay, so this is a category what we called as tri-monovalent. Tri-monovalent. Okay, and the electrovalency of the aluminum, that is 3, where is the electrovalency of fluorine, that is 1. So these how your where the aluminum have a configuration 2-8 and this also have a configuration of 2-8. So both get octet stability. So this is how your ionic bonds are formed. Ready? Fine. The next point. Ionic compounds are exist as an entity. Ionic compounds are exist as entity. Okay. So usually empirical formulas of ionic compounds are representing instead of molecular formula. Usually empirical formula of ionic compounds are representing instead of molecular formula. Okay. What does mean? What that statement means that actually, if we have a sodium chloride crystal, then there will be n number of Na plus and n number of Cl minus. This is the actual formula of sodium chloride. Okay, but we usually represent the Na plus Cl minus. This is actually empirical formula, the simple formula of that typical ionic compound. Okay, ready? Empirical formula. Ready? This is not treated as a molecular formula. This is simply empirical formula of that compound. Okay. So usually ionic compounds are exist as entity, where the empirical formulas are usually representing, and its mass is said to be formula mass. Ready? And I think that is familiar with your some basic concept in chemistry. You know the term formula mass. The next point. Since the force of attraction of constants in an ionic compound is balanced, the molecule have no specific direction. Since the force of attraction in an ionic compound is balanced, the molecule have no specific direction. Okay, that means, we have Na plus surrounded by what? Cl minus, lot of Cl minus. Na plus which is surrounded by lot of Cl minus. Actually, in the structure of NaCl, Na plus is surrounded by 6 Cl minus, right? Okay, so the net force of attraction will be 0. So there is no distortion from the lattice structure. Okay, so there is no particular direction to that species. That's why it is known as non-directional bond. Okay, so write that point. What it is? Since that net force of attraction is 0, there is no specific direction to the ionic compound. That's why they are called non-directional bond. Ready? Fine. So next, put an heading: factors affecting ionic bond, or favorable condition for ionic bond. That's better. So give an heading: favorable condition for ionic bond. Favorable condition for ionic bond. Okay, I think you are familiar with the thermodynamics and classification of elements. So this is very easy. Listen, what are the favorable condition for the formation of an ionic bond means? We know that here is a metal and non-metal. The metal have a ready tendency to lose electron. Then only the bond forms more easily. Moreover, if the metal loses electron, then the non-metal should have a greater tendency to accept that electron. Then only that forms a compound, right? So it means that if A is a metal, then A should lose electron very easily. Okay, and B is a non-metal, then B have a greater tendency to accept that electron to become B minus. Okay, ready? Moreover, they should combine to form a AB solid. That's also important. These all are the different conditions. Form the lattice. Once a cation and anion is formed there, they should readily combine to form the lattice. These three conditions are, which favors the formation of ionic bond. We can define the tendency to lose electron in terms of ionization energy, right? If a metal have a ready tendency to lose electron, means the metal should have low ionization energy. If a non-metal have a greater tendency to accept electron, means it means that it have greater electron gain enthalpy. If a cation and anion forms a lattice where the formed a lattice where it have to form, if there is a cation and anion and they're ready to form a lattice, means a greater tendency to form a lattice, means the stability or the strength of that lattice, that depends on what? Or the tendency to form a lattice, that depends on the amount of energy released while the formation of lattice. Okay, and that amount of energy which is released in the formation of lattice is called lattice energy. Okay, so lattice energy should also be high. Then only the forms a perfect ionic compound. Okay, so these are the conditions for the formation of ionic bond. Okay, your metal should have low ionization energy. Your non-metal should have high electron gain enthalpy. Moreover, the crystal should have high lattice energy. If these conditions are satisfied, then the ionic bond will be a more stronger and stable ionic bond. Ready? Fine. Okay. So let me define some more ideas about the lattice energy. Okay. What do you mean by lattice energy? I think you're familiar with that in thermodynamics and Born-Haber cycle like that. Okay. Lattice energy, we can define the lattice energy in two ways. Either lattice dissociation energy or lattice association energy. Lattice dissociation energy means the amount of energy required to break the lattice, where lattice association energy means the amount of energy to form that particular lattice, right? Okay. So both are equal and opposite, right? You know, both the magnitudes are same, but the direction, sign will be different. So how can we connect the lattice energy in terms of charge and distance? We know that if this is a crystal lattice, if this lattice is a stronger one, then stability and strength of lattice. If this is a strong lattice or more stable lattice, which means its lattice energy will be higher. Okay. Once this lattice formed, there will be a greater amount of release of energy. Then only this lattice become more stable. Okay. And if that particular amount of energy is supplied from, for example, if a lattice is formed from any kind of anion or cation, the energy released is minus 100 joule. And at the very same time, if another lattice which is formed where the energy released is 1000 joule, minus 1000 joule. Okay, which one is a strong lattice? Means this is a strong lattice, because if plus 1000 joule absorbed by that particular lattice from the external surrounding, then only the lattice broken. Up to that much, but here only required 100 joule. Okay, so lattice energy comparatively lower means the lattice strength is also lower. Okay, fine. So that's the idea. If a greater amount of energy released once a lattice formed, means that much energy the lattice have to absorb to break. Up to that, the lattice is stable. Okay, fine. So listen, and what factor that depends on the lattice energy? Lattice energy, no doubt the lattice energy that depends on the force of attraction between the constant ions. And the force of attraction between the constant ions, we all know that is Coulombic force of attraction. So lattice energy that depends on electrostatic force of attraction, which means lattice energy that is proportional to charge. Electrostatic force of attraction that is proportional to charge. So lattice energy that is proportional to charge and inversely proportional to distance. Inversely proportional to distance. Distance means the radius of cation plus radius of anion. Okay. If some questions are there to arrange the following in the lattice energy order, then you can use this criteria. If greater the charge, greater the chance for force of attraction, which means greater the chance for lattice energy, greater will be the stability. Okay. Lesser the distance, then the greater the chance for force of attraction, then greater the lattice energy, greater the strength. Okay, fine. So this much is enough for your ionic bonding. In this chapter, we are dealing more about the covalent bond. Okay, so first we can discuss the all bonds in a basic pattern like covalent bond, coordinate bond, metallic bond, like that. Then we can discuss the all others. Ready? So that's all about the ionic bonding. So next I want to move to the covalent bond.